Hi everybody, so today we're going to be doing our second set of notes for using derivatives to analyze a function. Remember, we're still trying to answer questions about the original function f of x, but we're answering those questions by looking at the derivative that we're given. So today we're going to talk about how we can use the second derivative to answer some of those questions. Just like the first derivative tells us specifically about the slopes of the original, the second derivative tells us about something called the concavity of the original. This means we can tell when a function is concave up, which means it's shaped like a cup, or concave down, which means it's shaped like a frown, by looking at the sign of the second derivative. So here's what concave up looks like. Concave up means it's shaped like a cup. What that really means is that the graph could look one of two ways. It could be concave up but going downhill, or it could be concave up but going uphill. We say that a function is concave up because the second derivative is greater than 0. Or, a lot of times we can't say that because we don't have the second derivative, we only have the first derivative. So the other option to justify your answer here is to say the first derivative is increasing, which means it has a positive slope. Now for concavity, we're always going to use parentheses because there's no equal to in the definition. It's just a greater than. The second thing we're going to be looking at today is the idea of concave down. Now we say that a function is concave down when it looks like a frown, which really means it could look one of two ways. You could be concave down but going uphill, or you could be concave down but going downhill. Either way, it's a piece of that frown. We say that a function is, this should say concave down, I apologize, because the second derivative is less than 0, or if we don't have the second derivative and all we have is the first derivative, we say because the first derivative is decreasing, which means it has a negative slope. Again, we always use parentheses when talking about concavity. Last but not least, just like yesterday, we talked about the special points where we change from increasing to decreasing as being called critical points. The special places where we change the concavity are called points of inflection. So these are going to be places where the concavity changes. We say that a function has a point of inflection because f double prime of x changes signs. In other words, it used to be positive and now it's negative, or it used to be negative and now it's positive. Or if we don't have the second derivative and all we have is the first derivative, we say because f prime of x changes from increasing to decreasing, which is also reversible. You could say from decreasing to increasing. It just depends on what's happening in the picture. So just like yesterday, we said, how does the graph of f of x talk about concavity, and how does the graph of f prime of x talk about concavity? We're going to do the same thing today. So in this first graph, which is the original function, we're going to be looking first for where this graph is concave up. Now this graph is going to be concave up for this entire lower part of the graph. That entire part of the graph looks like a cup. So we would say that this function is concave up from pi to 2 pi, and we would say because the second derivative is greater than 0. If I was looking for where this graph is concave down, I would be looking for where it looks like a frown. So I would be looking at the first part of the graph here, which is a place where we're concave down. And I would say that that's from 0 to pi because the second derivative is less than 0. Now, as far as points of inflection are the place where the concavity changes, which is going to be right here in the middle. So I would say that there's a point of inflection at x equals pi because f double prime changes signs. Now, interestingly, we are often given the graph of the derivative and asked these same questions. So in this case, I've been given the graph of the derivative. So this was the original, and this is the derivative. If you're looking at the first derivative, but you want to ask questions and answer questions, and you need the second derivative to do that, then you need to look at the slope of the first derivative. The second derivative is just the slope of the first derivative. So I'm going to be able to determine where this graph is, where the original graph was concave up, by looking for where the first derivative has a positive slope, which would be this portion of the graph. So what I would say is I'm concave up from pi to 2 pi because f prime, the first derivative, which is what I have here, is increasing. Now remember, increasing is just a shorter way of saying has a positive slope. If I was going to answer where the original function is concave down, I would be looking for where the derivative is decreasing. So I would say that I'm concave down from 0 to pi because the first derivative is decreasing, which means it has a negative slope. If you ever want to answer questions about the second derivative using the first derivative, we need to look at the slope of the first derivative. Last but not least, the point of inflection would be the place where I change from going downhill to uphill or uphill to downhill, which would be this point right here. So when x is pi. And I would justify this by saying because the slope of f prime changes signs. And again, this goes back to if you're talking about the second derivative using the first derivative, you have to look at the slope. Let's look at some example problems. So the first example problem is going to be, what if I give you the graph of the original? How would you talk about points of inflection, concave up and concave down? So let's start with concave up. I think that's probably easier than starting with points of inflection. My graph is going to be concave up when it's shaped like a cup. So that would be right here. And I'm just going to kind of estimate where to start this section of the graph. I'm going to do my best. It's going to be about -1/2. So I would say that my function is concave up when it looks like a cup. So I would say from -1/2 to infinity because the second derivative is greater than 0. Now I'm going to say that I'm concave down when my graph looks like a frown. So that would be about right here. And I would say that's from -infinity to -1/2. And I would say because the second derivative is less than 0. Last but not least, the points of inflection would be the places where the concavity changes, so right here in the middle. So I would say at x equals -1/2 because f double prime changes signs. Let's say, for example, I'm given the first derivative graph instead of the original. Well, my concavity is going to be determined by looking at where this graph is going uphill or downhill because the slope of the first derivative is the second derivative. So I'm going to be concave up during this section of the graph where I'm going uphill. That's going to be from -1/2 to infinity but I can't use the second derivative as my justification because I don't have the second derivative here. I have the first derivative. So I would say because the first derivative is increasing. In other words, the first derivative has a positive slope. I'm going to be concave down when the first derivative graph is decreasing. So I would say I'm concave down from negative infinity to negative 1/2 because the first derivative is decreasing. In other words, it has a negative slope. Last but not least, points of inflection would be the place where that changes. So that's going to be when x equals negative 1/2 because the second derivative, I would say because f prime of x changes from decreasing to increasing. It changes from downhill to uphill. Last but not least, what are you going to do if I give you the equation instead of the graph? Well, we're going to start in a very similar way to what we did before, which is if we want to answer questions about the second derivative, let's find the second derivative. To do that, I'm going to take the derivative of the original function, which is 6x squared plus 6x, and then I'm going to take the derivative again, which gives me 12x plus 6. I'm going to set that equal to 0. Because just like with critical points, setting it equal to 0 will help me determine where this function changes concavity. If I factor out a 6, I get 2x plus 1, which means if I solve this, I get negative 1/2. Now, just like in the past, we made a chart where we had the signs of our first derivative in the chart, we're going to make another chart, but we're going to be looking at the sign of the second derivative here, because concavity corresponds to the second derivative sign. So instead of putting f prime here, I'm going to put f double prime. Now if I pick a number less than negative 1/2, like negative 10, and I plug it into this equation, I'm going to get a negative number. If my answer is negative, then that means the original graph was concave down. So I'm going to draw a little picture of a frown. I'm going to pick a number bigger than negative 1/2, like positive 10, and when I plug that in, I get a positive answer, which means the original graph was concave up. So I'm going to draw a little picture of a cup. Now I can use that chart of the second derivative values to answer my questions. I'm going to say that my function is concave up from negative 1/2 to infinity, and I'm going to say that's because the second derivative is greater than 0. Now you'll notice that this time I could answer the question using the second derivative because this time I could actually calculate the second derivative and use it. I'm going to say that my function is concave down from negative infinity to negative 1/2, and again I'm going to say that's because the second derivative, which I could actually find now, is less than 0. And last but not least, I'm going to say that my points of inflection are at negative 1/2 because the concavity actually changes signs there. So I would say because the second derivative changes signs. Last but not least, let's look at a couple example problems of what is very typical on the AP test. So one classic AP question would be a problem like number 4. If y is a function of x such that the first derivative is greater than 0 and the second derivative is less than 0, which of the following could be a part of the graph? If my first derivative is greater than 0, it tells me that the graph I'm looking for must be going uphill because it must have a positive slope. And if the second derivative is less than 0, it tells me the graph that I'm looking for must be concave down. So I'm looking for a graph that is always going uphill and is always concave down. Now, as a reminder, concave down could be just like this or just like this, just part of that curve. Since my graph has to be going uphill, the part of the curve that's going uphill means it's always going to look like this. The only graph here that meets that criteria would be option B. For problem 5, again, this is a classic AP question. We've got a function that's differentiable. Which of the following is true? Now, if you look at the answer choices, we are looking at the place where x is 1, and we're comparing f of 1, which is the y value, f prime of 1, which is the slope, and f double prime of 1, which is the concavity. So let's do those one at a time. We're going to be looking at f of 1, f prime of 1, and f double prime of 1. F of 1, because this is the graph of f of x, would just be the y value of the graph. If I go to where x is 1, the y value of the graph right there is 0. F prime of 1 would be the slope of the graph. Now, I don't know the slope exactly, but I do know that that slope is a negative number because this graph is going downhill. And last but not least, f double prime of 1 would be the concavity. Now, I don't know the value of the concavity exactly, but I definitely know it would be a positive number because this part of the graph is concave up. So because of that, I can say that if I were to put these numbers in order from the lowest to the middle to the highest, the slope, f prime, would be the lowest, the y value would be the middle because that's 0, and the concavity would be the biggest because that's positive. That means that I need to find the option that has f prime of 1 first, it needs to have f of 1 second, and it needs to have f double prime third. That means I'm looking at option C. So I don't really need to know the exact numbers, I just need to know that one of them is positive, one of them is negative, and one of them is 0. We are going to save the last two examples to do in class so that this doesn't become a very long video, and I will see you guys tomorrow for some practice. Thank you so much for watching.